All right, guys. Good evening. Can you hear me? Can you see me? Can you see the slides?
Yes.
Yes.
No. Yes, everything is okay.
All right, good. Well, we got 51, 52 participants out of 100, 120, I think. We wait for one more minute and then we'll get started. All right, guys. So let's get going. Today, the second lecture on our course Data Science for Business, and this lecture is Introduction to Machine Learning. And it looks like I'm the only one with a camera on, but I mean, if you turn on cameras on, it would be great. This lecture is really an introduction to machine learning, and so if your background is in computer science, might not be the most interesting for you, so you can actually skip it. But for everybody else, this is a very, very concise introduction into the field of machine learning, the techniques that we'll be using. And later on, as we go through the course on different lectures, we'll dive in deeper into those techniques and discuss, their applications and how to do it. Now, at the seminar or lab sessions, you will have a chance to practice some of those techniques. Again, this is sort of, very broad, very sort of general introduction. We'll talk about those techniques in more details when we start doing case studies. All right. So first of all, what's machine learning, right? Now, if you think about a discipline as a sort of computer science as a discipline where people deal with writing algorithms, writing programs, pretty much all the computer stuff, then you can think about this as a sort of as artificial intelligence being a subfield of computer science. And machine learning is inside artificial intelligence. It's a subfield of artificial intelligence, or sort of we can talk about the techniques there. And the deep learning, you probably heard about that too. It's part of some of the techniques that I use within machine learning. Now, AI today is a ubiquitous word and everybody talks about it. Every company is using AI or says they're using AI. Right? Typically, by artificial intelligence, we understand intelligent agents that are capable of setting certain goals and reaching those goals. So that sort of type of program. Now, in fact, most of the companies today, they're not using AI, they're actually using machine learning. And machine learning, the techniques and algorithms that it provides that teach computers how to achieve certain goals. It is not, and I should be very clear here, right? Whatever we have today in machine learning is not an intelligence, right? And so we're not going to be touching on that subject whatsoever. You might heard a lot of companies saying, yeah, we use intelligence here and there. What we're going to be talking about is actually a set of algorithms, very well defined, operating on data that allows us to predict certain things, but this has nothing to do with intelligence. And I can assure you that for today, we actually do not have artificial intelligence. So it actually does not exist as of today in terms of intelligence, understanding human kind of intelligence, right? So it is more of a buzzword. So speaking about techniques, we're talking about machine learning, and so I'll be using terminology of machine learning. And machine learning algorithms, these are algorithms that analyze data and can detect certain patterns in the data, and based on that patterns makes predictions. And predictions can be into the future. So you can think about time being as being an axis in those predictions, or it can be used, predictions can be used to fill in, for example, certain gaps within the data. That is also a prediction. So pretty much anything that is not given in your data, whether it is sort of looking forward, looking backward, or sort of for the data you have at hand, can be predicted with certain quality, and that's what machine learning is really doing. Now, I think there is also quite important slide where I'm trying to explain sort of what's the difference in between sort of traditional programming and machine learning, right? The difference is really simple. In traditional software, the software that has been written for I don't know, more than 50 years now, right? Typically, it operates on the rules that are hard-coded by people, and it uses some data, and based on the rules that are in there, based on certain sort of algorithms and sequences of rules and processes, produces some answers or actions. And that's sort of the core of pretty much any software that's being used everywhere. Now, what we understand today by machine learning, and the machine learning software is really pretty much creates rules from the data. So here it's not people who give the rules, it is an algorithm that creates rules from the data. And those rules can be explicit, and we'll see examples of that, or implicit, so it's not written out, but it's sort of created in internal representation. And again, when people talk today about AI, well, they're actually talking about the software that can learn, and that's machine learning, right? So here, we typically provide data, we typically provide some examples, and then the algorithm creates rules, or we often call those rules the models, right? A model or models. And that's the principal difference. So instead of giving instructions to the software, we give software examples and let the software generate the rules and create a model. So typically, when we deal with machine learning models, there are two phases, right? So one phase, the first phase, is actually sort of model design, putting together an algorithm, and then training. Now, model design and putting together an algorithm is usually consists of feature engineering and other steps. We'll talk about them more, of course. But then when you design the model, you want to train it. And training the model is really about determining certain parameters in the model. And then we need to verify that what we have done actually operates, and so we need to test it with some data. Giving an extremely simple example, your model can be a linear model, which is a line, and the line is defined by a set of coefficients. And so, for example, model design could be a selection of a model which is a linear model. So think about it as a line or a plane. And training will allow us to select coefficients for that line, right? Well, if you think about a sort of situation with one variable and one result, right? It's the position of the line, two variables, right? Two parameters, and then we'll train it, and then we'll determine those parameters, and then we'll verify that this is the right parameters found. And after that, we can use it, right? We can use that model for prediction, taking new data and then predict some results. So as a data scientist, you're usually working most of the time on the first phase, which is a model design, training, testing model. And then you give it to production people who actually, make use of this model. So here is a very, very, very simple example. let's say you have some historical data about, there's some sort of numerical values there and categorical variables X, Y, Z. And then there are, for example, some sort of labels, accepted, rejected, let's say some sort of offer that being given to the customer, and there are some parameters. And we take this data and we choose a type of algorithms we want to build. Let's say we want to use decision tree. We'll talk about trees in depth later, but let's say it's a tree and it's really a decision tree. And the role of this algorithm will be of the training of the algorithms, or the goal of the training of the algorithm will be to build this tree. So we select the class, which is a tree, and then we need to construct it. So you're taking historical data, and through the phase of modeling and training, you construct this decision tree. Then, whenever you start using it, you take a new data point, and you just sort of go with the data point through the tree to predict the result, because typically in the decision tree, the results lives in a leaf of the tree. And so the first phase, construction, is usually we talk about model training, model building. Sometimes you talk about mining the data and creating the model. But that's the part you spend most of your time on. And then this is model application. Of course, as a data scientist, when you train the model, after you created this tree, you want to test it, and we'll talk a little bit more about it later. You want to test it, and that's where you sort of use it as a data scientist. But eventually, when it comes to actual business, you pass to the production your model. And then this model is being used on new data in the real world setting. So when we talk about machine learning, it's really this triad of data, because you need to start with the data, algorithms, sort of the set of algorithms, the sort of world of possibilities, what algorithm you choose, and then you train those algorithms on the data. And sometimes you talk about training algorithms, or sometimes you go talking about learning, sort of making algorithm learn from the data. But in general, the point is always the same. You want your algorithm to detect patterns in the data and then generalize them. When I say generalize, it means try to predict what happens in the data points, those that you haven't seen. So if you think about, again, sort of regression settings, it is either interpolation or extrapolation, if you remember those terms from some of your basic math. So we either try to predict what sort of happens in the empty gaps, inside the data set, or maybe sort of outside of the data set. And again, we'll look at some more examples on the next couple slides. So previously we talked about those three types of machine learning: supervised, unsupervised, reinforcement learning. We're going to be focusing on supervised and unsupervised learning, where supervised, again, is when you're given a set of examples, or being more formal, you have a set of inputs and set of outputs, and you learn the mapping from input to output, right? And input is usually called independent variable, output is dependent variable or response variable. When you have unsupervised learning, you do not have an output, you're just trying to find patterns in the data. I would say 90% of the usage in the real world is really on the supervised learning. So that's sort of the workhorse of what's being done, what's being used. So if we dive a little bit deeper, then supervised learning, you can classify it into, well, two main sort of two main directions. It's a classification, two main type of algorithms. It's a classification and regression. The difference is regression is an algorithm which tries to predict numerical values, numbers, and classification tries to predict classes. Sometimes it's binary, sometimes it's multi-class values, but it's it's prediction of the classes. And there are a bunch of different algorithms exist for each of the type. For classification, there is a decision trees, and that's probably like sort of the most well understood and sort of most widely used algorithms, and sort of decision trees, and then so-called ensemble methods, which is usually group of trees, etc. And then there are some other methods like SVM, support vector machines, bias methods, and of course, neural networks. Yeah, we will talk about them a little more, about neural networks and deep learning being sort of one of the representatives of the new classes of neural network. Regression, if you notice, there are a lot of the same methods, and I'll try to show you later that's pretty much, classification and regression. Yes, these are just two sides of the same thing, and like most of the algorithms that you can use for classification, you can use for regression, like support vector machines is a classification algorithm, but there is also support vector regression. Decision trees can be used for classification and regression. Pretty much all of them can be used in both settings. Now, unsupervised learning, these are sort of two main, I'll say the main division is, in clustering, which is automated or, sort of self-finding of groups of points that have more common among them than with the rest of the data. And another class is dimensionality reduction algorithms. These are the algorithms that allows you to reduce the number of variables that are used to describe the data. An example could, and we're going to talk about them. Example could be, for example, you have 3 variables and you kind of want to encode most of the information into using only 2 variables. You're going to lose some information by doing this, and dimensionality reduction gives you a way to sort of minimize those losses. Manifold learning, as an example of dimensionality reduction is, for example, principal component analysis, or there is also all kind of manifold learnings. Talk about it later in the course. But if you use, there is a sort of statistics on the left-hand side, based on the reviews that sort of the top algorithms methods that are used by data scientists. And if you notice, it's regression, it's classification, which is decision trees or rules, and it's some form of clustering, right? So these are like sort of the things people use most in their daily work. So giving this overview, I just want to give you some examples. So to sort of anchor this on some thoughts, on some ideas that help you remember those things, right? So supervised learning or regression. As I said, supervised learning is really about predicting numerical values. And, you didn't know that what you did back in high school or maybe first years of college in math is actually called a regression, where you have multiple data points. And let's say here on the left-hand side of the slide, we see, and I can probably use pointer here. Let me try. All right, guys, can you see my pointer, the red one? Yeah, okay. Right, so here on the left side, there's a simple example, sort of univariate, which it means there's only one variable. Its dependencies, for example, on sales of some item as a function of TV advertising costs. And here, you have all the data points, and you want to find sort of a line that describes the data, right? You notice that the points are scattered, but you can probably draw a line, and we'll discuss later the way you can do this. Now, why would you want to do this, to draw the line? Well, because, for example, you might have sort of all the data points, but you might not, for example, have a data point supposed at let me find drawing. Okay, let's say you don't have a value for this one. Well, you don't have a data point for this one, so you interpolate, and you might get the answer. Or, for example, you want to spend that much money, and you're expecting, what will be the sales? Well, to do this, you kind of extend this line, and that gives you a prediction on what the sales volume would be. Plus, also, if you notice, the data points are quite scattered. So even if you have, for example, let's say you spend on TV advertising 200, whatever units are, there are sort of different values. There are probably different occasions you will get different volume of sales for the same kind of spending. Well, how do you decide what the right value? Well, again, this line helps you pick up the average in this case, right? And so that's the simplest regression, right? And this is example of supervised learning. On the right-hand side here, we're looking into two-dimensional, where, for example, we try to calculate dependence of income on years of education and the seniority. And if you notice, here we're not trying to show you a straight, well, in the case of two dimensions, it's going to be a plane. So this is not a plane, this is sort of curved manifold that describes the data. And again, it allows us to predict the values, the income at the value of education and seniority that we didn't have. And if in one dimension, you quite often, pretty much for any values of that, you might even have a data point, then the higher dimensions you go, and the dimensions meaning the more variables you have in your function, right? The more variables you have here, say years, education, seniority, etc., the more chances that original data will not contain the result you want, and so you need to find it through this type of interpolation. And so, again, on the left-hand side, it's linear regression. On the right-hand side, it's nonlinear regression. But this is example of, the regression problem. Classification, which is second example within supervised learning. It's probably, this is like sort of two examples. On the left-hand side, let's say we have samples. As I said, the point is we do have samples of the data points, right, of objects in this case, for example, class yes and class no. And here's examples. And then the goal is to somehow classify the new object into one. I can see the hand, I'll ask you in a second. You can classify into one of those two binary classes. As for example, this blue half moon, should it belong on the left-hand side or on the right-hand side? And algorithm, by the way, where do you think it belongs to?
Left.
Left, why?
Because of the color.
All right, yeah, so there are two things, there are two factors here. It's a shape and color, right? And we can see it's shaped as half moon. There is no half moon in either of the example set, but if we look at the color, there's a color in the blue set, so clearly this will go to the blue, right? Now, with this, arrow, well, that's a good question, because on one hand, there is an arrow here. On the other hand, there's a blue color in there. So depending on which feature is important, it might go, either way, right? So, and that tells you that, sometimes, the classification will not be perfect always. And then you can also go for multi-class classification problems, where, like here, you have this handwritten digits, and the question is to classify it into, well, classes, which is the digits, and do it automatically. And for example, here it shows that yes, this picture has been classified to the class 2, class 7. This picture has been classified to the class 2. This picture has been classified to the class 1, etc. Sort of another example for the classification for the supervised learning, which is more business-like. Let's say we're trying to predict if somebody is going to default on a loan, and let's say that depends on the balance on the checking account and, for example, person's age. And we run the algorithm. We build the decision tree that tells you that based on those two features, two variables, you can actually predict, if somebody is going to fail default on the loan. Let's say somebody's age is 40 years, 40 years old, and the balance is less than $50,000. Then we can take this model that we build and say, okay, if it is less than 50,000, we go here, and if it is less than 40, let's say 40-year-old less than 50, it goes here. And so it actually gives us a very high probability of write-off, so which means it's most likely the default. So that's sort of another example of classification. So we build the model and on the bottom, what we're showing here, this is sort of a bunch of data points that are being used to train this model, and that's how it's sort of prediction the space of balance and age. So there is a hand up there. What's your question, please?
I have a question about efficiency and accuracy supervised learning in terms of what if we will give, first of all, the primary information and it will be, for example, with all answers yes, if we will think about yes and no answers. So we will intentionally learn our model to answer us only yes, for example. And then our data, we will lie to ourselves. Is it correct? For example,
your example is correct, but this would be a very, very poor modeling, and we're going to talk about this. What we want to do is we want to have what's called balanced classes in an optimal world, which means we want to have the same number of positive and negative examples, right? If we just give you only positive examples, of course, algorithm will always learn only positive things. So you need to algorithm learns sort of the boundary, the contrast in between two types of examples. If it's only one type, one class is given, of course, it's not going to work. All right, let's move on. So I also wanted to point out that regression and classification, they're pretty much the same thing, right? Let's look at the left picture here. This is sort of example of very simple linear regression where we want to predict a numeric value, right? So, and X and Y's, a bunch of data points, we try to draw some line, and based on this line, yes, if I pick up some value here, I can predict, I can predict from X, I can predict for any X, I can predict Y. Yeah, that's a classical regression problem. Now, let's look on the left side where we have a classification problem. Classification problem here, if you remember, there is X given, and then there's a binary response, either one class or another class. And I can code classes as being class 0 and class 1, right? Those curly braces means there are just only two values, 0 and 1. It's a set. And so, what it says here, if the X value is, for example, -1, that it belongs to class 0, right? And if X value is, for example, I don't know, -2, it belongs to class 0, but if X value is, say, 0.3, it belongs to class 1, right? This is class 1. I don't know if X is equal to 2, it belongs to class 1, etc. Okay, so it's pretty much the same as on the left-hand side, except for there are only two values, 0 and 1. Can I do regression on this? Yes, absolutely. I can draw this blue line, right? but it's probably not describing too well the answer, because I want to predict the actual class, right? I want my prediction to be either 0 or 1. And if I come up with this, and try to do something along this line, well, it will predict me sort of any possible value. And here it will go, to minus infinity and to plus infinity. But nobody forces us to do, the straight line. We can, for example, use this curved line, the red one I showed here. It's in fact called logistic regression. And it kind of smoothly goes from 0 to 1. Approaches 0 here, approaches 1 there, and sort of goes pretty much where this blue line would go anyway. And then you can say, for example, okay, we can put a threshold right here at 0.5. And any of the prediction that we do, let's say we take this value, that's the value that it predicts. It's less than 0.5, less than threshold. We'll call it class 0. We'll take this value. It is less than threshold. We'll call it class 0. We take this value. It predicts here 0.8. It's more than 0.5, so this is going to be class 1. We take this value. It's going to be class 1, and so on. So pretty much we used regression with a certain type of function, which is it's called logistic regression, to solve the classification problem with two classes, binary classification. So, and that's why a lot of algorithms that I used for regression can be used for classification, and that's pretty much sort of the same type of algorithms. If you build a decision tree, you can put numerical values, you can put categorical variables there. Okay, that was a very, very brief introduction to regression, classification. Again, if this is the first time you guys meet that terminology, well, so first of all, welcome to this world of machine learning and models. Then we'll be going in depth with each of those models, and you will learn in the case studies how to use them. Here, I'm just trying to give you sort of this broad picture, sort of overview of what's out there, and give you some sort of basic concepts. You're going to kind of understand them better later on. Right now, it's sort of you're meeting them for the first time, right? Okay, another very important concept that we have in machine learning is good model and good model fit. And people often talk about model sort of overfitting. So the idea is when you have data, you need to select the complexity of the model that is good for your data. And this is sort of the art. It's an art form, right? After a while, you're kind of getting used to, and after you've seen a lot of problems, and you know how different models work, you intuitively can understand which model can work for each data. But conceptually, if you look at this picture, I'll try to explain to you what I really mean here. Imagine that these are your data points, right? And they're not, they don't follow a straight line. But can we model them with a straight line? Yes, we can, right? But is a straight line a good description of these data points? Well, probably not the best one, right? Because if we try to predict here, if I take the value, it will predict me here, but the actual value is there. So it's, we're pretty much significantly off. The same thing, if I choose this guy, the real value is here, and the predicted value will be there, also very much off. So, and I mean, it's obvious from this picture that, the straight line does not describe the data too well. Okay. Now, you can do something different. You can create the model which goes through each data point, right? The way the sort of red one does. And this model perfectly describes the data that we have at hand. But the trouble is, when we collect the data is quite often is noisy. And so, though we have the precise values in the computer, those values by themselves might not be the right values for the actual process that we're trying to describe. Simply because there is noise, right? You measure height of somebody, well, there is plus minus certain centimeters. You measure weight, there is a mistake. I mean, whatever you take the measurements in the real world, there's always mistakes in that. And so you do not want to precisely reproduce the data points you have at hand. So that's one point. Other point is, you want to be able, your model to be, it's called generalization. You want it to be able to generalize smoothly, because again, in most of the real data sets, data points, there's almost never sharp changes, right? It's usually things are smooth. So on the left-hand side, too simple. This is just too complex, right? It works very well on the test data, but it most likely will fail in the real world. And so you want to pick up the model that, yes, describes your data well, but at the same time is not extremely complex, right? So this is too flexible. This is, too inflexible, too simple. This is too complex. This is just right, okay? How to do it, and depending on the type of the model you use, it is, it's different parameters that control the complexity of the model, and you're going to learn this. But let's say if it is a line, right? It's a degree. If it's a polynomial, the way we show here, it's a polynomial, right? It's a degree of polynomial, which is, if it is x squared, x cubed, etc., etc. If it is a tree that we want to build and describe things, it's usually the depth of the tree, so how deep it is, and etc., etc. So in every type of model, if it is a neural network, right, it's also the depth of the neural network. And so depending on the type of the model, there is always a parameter that controls complexity. And the models are too complex. Well, first of all, you need a lot of data to train them. Then they're unstable, and they usually, they unfortunately tend to model noise instead of sort of actual data. So, but if you do something very simple, it might not work either, because you produce not very accurate results. And so, the art form in data science is to actually select the just right model for your data, but also just right model for your business problem. Because sometimes, even very simple model might work well, and then you just, will be wasting time and resources trying to build something more complex. Here is another example. When we have those two classes to solve the classification problem, blue and red, it sort of feels like overkill to draw this green line, right? It perfectly separates those classes. But this, for example, this blue point, this one is clearly sort of in the wrong part, right? If you think about the sort of the separation between those two classes, and this is somehow sticks in here. So you probably don't want it to be called a blue, right? It's probably due to noise or some other errors in measurements, and so most likely the actual boundary separating classes is this thick black line. Again, it's very easy to visualize and understand this when you have a two-dimensional problem, right? It is much, you cannot, if you have 50 dimensions, which means 50 variables, it's going to be much, much harder to understand what is just right. And we'll teach you some metrics you can use to understand that. Okay. So there is always, I mean, there's always in life, there's a trade-off, right? There is a sort of model explainability. So, you know, how simple model is and prediction accuracy, right? So you kind of, you know, can take, you can build this very simple model. If it's a tree or some sort of small tree or some linear model, that is very easy to explain. Again, it's used decision trees or logistic regressions, linear models. But they might not give you very high quality results, right? High quality results usually coming from more advanced models like random forest gradient boosting, neural network, deep learning stuff. But they're very hard to explain visually or to explain at all by the certain decision being made by those models. And so the job is quite often to balance this model explainability, what's called white box models and black box models, that give you good prediction accuracy, but poor explainability. Now, I'll give you an example. Let's say, you know, sometimes when you have a self-driving car, you want to do a very good job, you know, turning a little bit left, a little bit right, accelerate, decelerate. You know, you probably don't really care as a driver for your car to explain to you why it actually shifted a little bit to the left or a bit to the right. You know, what kind of triggered that shift, right? Or what triggered it to accelerate or decelerate. But if it's a model that, for example, used in medical image analysis and it's detected, let's say, some abnormal growth, a cancerous growth, yes, doctor want to understand why the model decided that this is a bad tissue, right? Because you want to trust the model in that case. So depending on the applications, you, as a designer of the model, you can either go for sort of simpler models, more explainable models, or more complex models that gives you high prediction accuracy, but they're harder to explain, you know, and more challenging to use. Usually, also prediction accuracy highly depends on the amount of data you have for the model to train. And say deep learning gives you actually amazing results, but it usually takes a lot of data and a lot of computational resources to train deep learning models. So they're of course used now in computer vision and text analysis, and there are like exist pre-trained models. But when you deal a lot with sort of day-to-day business problems, trying to predict sales revenues, I don't know, things like that, you usually go for the simpler models. And in this course, we'll be focusing more on sort of left-hand side on those simpler, understandable models. You know, regression. How do we model this? Well, let's say I select a particular type of model that I want to use, which is going to be linear modeling. Why? Well, because, you know, I look at the data, I think, you know, it's dependency on sales on the volume, on the amount of money spent in advertising. It's, you know, could be linear. Okay, I need some sort of baseline to do it. Okay, so here is the model that I think will be the right one. Now, how do I train this model? How do I actually find this sort of the angle? How do I find the parameters of the line that I have shown to you? Well, the way to do this in this particular case, and again, this is one-dimensional, so it's very easy to understand. For every point that we have, every point that are given to us, all right, we have input x values, we have output y values. For every point, we know what our model would predict for that x value. And this is our sort of error metric, or how much our blue line, our green line will be off from the actual value, right? So this is the actual value. This is what green line predicts. So that's an error. Okay, fine. We take the next point. Here is what's going to predict. This is the actual value. So this is sort of an error, right? This difference. For this guy, the same thing. For that guy, same thing. So if you look at all those, the straight line model does not predict perfectly, right? You add up those errors, and so these are pretty much the length of those lines. These are errors. You can add them up and say, look, this is a total error that you're going to have if you use a straight line as a model. And the way to determine the angle for the straight line is to minimize the error. And so that's how it's computed. Again, we'll go into details next time. But this is overall the idea. Now, when you create the best straight line, calculate the error for the best straight line you can say, okay, look, this error is just too big for me, for my business problem. Let's straight line as a model doesn't work. Let's go for example, second degree polynomial. Let's drop parabola or something. Now, I just said, look, let's just measure this deviation, this errors, and it's often called loss function. And just measure that length. Well, you can actually do this exactly as I said. Those length is called mean absolute error, and that's what you can calculate as a metric, quality metric for your model. Or you can calculate mean square error. There is slight difference here. You take some of the absolute values, which is just sort of these distances. This takes that distances squared. Well, it's more sensitive to outliers. For the most popular value and one we're going to use a lot is either RMSE, which is root mean squared error, where your prediction versus the actual value squared some square root from. Or it's extremely popular to use metric which is called R squared. Again, you'll be using it a lot, and if you did any statistics, I'm sure you've seen it, which is just this ratio of the values of the residuals, and the residuals is the difference in between the actual values and predicted values, right? Divided by the variance in the data, where y average is the average value in the data, and this is each data point, and so it just tells you how much variance is within the data. And if you think about this sort of for the baseline model, where you take the average as an answer, let's say instead of doing this this line at an angle, we'll take this line as an answer, so some sort of average, right? For this R squared will be a 0 for baseline model, and if the residuals is 0, which means model perfectly fits everything, then R squared will be 1. Now, R squared 0 is a bad idea because it means you just took an average. It's just too simple. But R squared equal to 1 is most likely also is a bad thing, because that in real life it never happens. It most likely means that you overfit the data. So typical R squared is probably around 0.8, 0.9. That's sort of the values that people use to work with. And that's how you deal with regression type of problems. With classification, if you look at this example, clearly there are 3 classes: blue dots, green dots, and orange or brown dots. Variables. Yeah, there is no clear class separation. I mean, it's very clear class separation of the blue class versus green versus orange, but there is no clear separation between green and orange. Here's another example. I think this is much better separation, and you want your algorithm, if you build the algorithm to find the sort of border lines that separates those classes. In this case, it's going to be sort of linearly separated, probably something like that. And any point that you find in between those 2 lines, those 2 green lines can be counted as the orange, and anything below, we can count the blue, and anything above we can count as green. And there are algorithms like support vector machines that will do precisely that. Or it could be some other algorithm that will, for example, try to find boundaries like this, which is also quite possible. So depending on the algorithm you use. Now, in case of classification, there is also a metric that we evaluate, trying to see if the algorithm are working well or not. And this is typical what's called confusion matrix, where we talk about what's called true positive, false negatives, true negatives. So what does it mean? Well, let's say, and this matrix works for binary classification, right? For two classes, and let's say class yes or no, class had not happened, and true positive means we predicted that the event happens, and it did happen, or predicted that the point belongs to the class one, and it does belong to the class one. True negative, we predicted that the event didn't happen, and in fact, the event doesn't happen and will not happen, or we predicted that the class is 0 and it is in fact 0. So there is true positive, true negative, and then there are false positives and false negatives. There are two things where you predict 1 and it happened and it is 0. You predict 0 and it is actually 1. These are sort of two options where algorithm fails. Today's example from today's life, you take a PCR test. It is negative and you don't have a virus. Okay, this is that's good, right? It can be positive test and you do have virus. Again, the test done well, but you don't have virus, but it says you have virus. It's false negative, and you don't have virus, but it says there is a virus. It's false positive. So pretty much in all those scenarios where there is this binary task and there is a prediction, well, you can use this quality to do the classification. And then, for example, one of the metrics that is widely used is called accuracy, which just tells you the ratio of correct predictions, whether it is positive or negative, but the correct predictions to overall total number of predictions that are being made. So that's how you evaluate classification. Now, very important point, if you never worked with machine learning type of problems. As I mentioned from the very beginning, when we train an algorithm, we want to verify its quality, right? It's very important. And to verify its quality, we need to do it on a data that algorithm has not previously seen or hasn't been trained on. And so typically the data that you have is split into the train and test set. Train and test split can be 80-20, 70-10, 70-30, 90-10, depending on how much data you want to use for test. But the algorithm should never see the test data until you try to test the algorithm. So you train it on the data, then you test it. Of course, you will verify algorithm on the training data itself, but the numbers you get there most likely, they're not useful. Performance of your algorithm will always be worse on the test set compared to the performance of the on the training set, right? But that's the way it should be. So you build, remember, if you go back, you remember this, for example, I showed you example of a tree, and if you want to use your data to train the algorithm, it builds a tree. If you run the same data you use to build the tree through this tree, it will classify it really well. But that is not going to tell you about the quality of the algorithm. You need to take the data that this algorithm, that the tree never seen and never been used to build the tree, run it through this tree, and then that will give you an example. That will give you more or less, quality metric for your algorithm. Again, just be aware that when later on you put your algorithm in production, most likely its performance will be even worse than the one you see on this test data, right? So performance on the algorithm on the trained data itself it is not telling you about anything. Performance on the test data, this is your method to verify things, and performance on, in the real world will usually be less than or worse than the test data. Now, having said that, yes, I see a hand, Alina.
Just a quick question. Inaccuracy, if I understand it correctly, will identify, how do we identify false positives and false negatives? Would this be by running our algorithm on the test data where we already have classified everything manually, and we're trying to see whether the algorithm gives us the same results that we have predefined, or how does it work?
Yes, absolutely right. You're absolutely correct. Remember, it's
Or we should wait for the actual testing. Yeah, just continuing the question.
Okay, so you're absolutely correct that when you have a when we work with supervised learning, you have remember you have examples, right, that already have labels, correct labels, and that's how you train your algorithms. So you save part of your examples, in this test set. You don't use it to train algorithm, but you know the right answers, right? And then you run them through your algorithm. It predicts the value. You know the right answer. You compare it, and that's how you build this matrix. Okay. Now, when you go and use it on
Professor.
Yes.
Then it is mandatory to have a real already resulted data, right?
Of course. That's why it's called supervised learning. You need to have examples. You need to have examples, verified examples that you can train on, right? So you need to know the truth, the ground truth to teach your algorithm. Okay.
Yes, thanks.
All right.
Can I just ask one quick follow-up question?
Yes, please.
So besides the training and the test data sets where we do know the right answers, when we use this algorithm on real world data where the parameters that we're trying to estimate are unknown to us, then how do we, in that case, how do we calculate the quality metrics of our algorithm, or how do we know if it's performing well or not?
So you calculate quality metrics, right? So remember right here, for example, right? So you build the algorithm where you already had the class values. You use that to construct the model, and you use so this historical data. Okay, so let me do this. You take this historical data, you split it, you use, for example, this part to build the tree, right? And then you use this part, you run it through this tree, and you get the accuracy of your algorithm, right? Accuracy. So then the tree is built, okay? You know its quality because you had the results already. You know what the correct answer is. Then you put it into production. When you put it into production, you don't know the class, it actually predicts the class. Now, if you want to check the quality within the production, you will need to find a way to determine the real class. It can be manual labeling or something else, and then verify it on it. Does this make sense?
Yes, thank you.
Okay. All right. I think I have like one more slide and then we'll done the lecture today. Okay. Now, but there is a catch here, and the catch is, it's kind of pity. I mean, to waste this part of the data, right? Because you would say, look, I mean, I need to use everything to make my algorithm better, because we talked about it. I mean, the more the data, the better your algorithm will perform, right? And here it feels like, look, we're throwing away from 10 to 30% of the data, right? We're just using it to check, but we're not using it to build the algorithm, right? To build the model, to determine the features. So that's why people most of the time they're using a slightly different approach. Instead of just splitting on the training and testing, they use what's called cross-validation. And this is the idea. The idea is that instead of just training your algorithm once, what you do is you split your data, and here I showed it split into 1, 2, 3, 4, 5 pieces, right? And you train algorithm on the first 4, and you test on this 5th. You train on the first 1, 2, 3, and the last one, and you test on this one. You train on these guys and these guys, and you test on this one, etc., etc. It's called five-fold cross-validation. And then you average the results, and that gives you average performance of your algorithm. And then before you go to the production, you train it on the entire data that you have. Okay, that's what you do in practice. Make sense? Okay. Okay, so going back to sort of the beginning of the lecture, when we have the supervised learning pipeline, training and model application, you start with your data, right? You have this X, Y, Z values, whatever features we have as an input. There is a label, which is a class label, which is the correct answer, right? Then we do this feature extract or feature engineering, we have features, and then we train the algorithms. Then we take the model that we created, that, for example, the tree, and that goes into multiplication or production. When you have an input, we do not have a label, we don't know it. We do exactly the same type of feature engineering, and we'll talk about it a lot, how to do feature engineering. You send it through the model itself, and it will generate for you the right label. If it is regression, the label is just a numerical value, and you'll get sort of numerical value at the end. So again, there is this model training, and you train the model when you have on the data that have labels, and then you verify quality on the same data using cross-validation, and then you use the model, put it in production, or it's also called model application on a raw data with no labels, right? And then you predict the labels. And here you cannot evaluate the quality right away, because unless you know the correct labels, if you want to after a while, if you want to check the quality of the model, you will still need to get some labels from somewhere and run it through this. Then it will evaluate the quality. And this is sort of traditional, typical supervised learning pipeline. Again, we're talking about supervised learning because that's sort of what most of the business applications doing one way or another. So 3 steps, prepare data, where we define problem and choose the model, getting the data, understand the data, clean the data. Then we build the model, and this is feature engineering. And you will talk at the seminar about feature engineering. You build and you test the model. You try to understand the performance of the model in various conditions. If needed, you iterate, and later on you take it and put it into production. You understand, you explain what this model does for the business. You look at the changes that you need to do in the business to use this model. And the last and very important thing, this is, by the way, what you are asking, you do need to do ongoing monitoring. So you use the model in production, you use the model in business, but once in a while you need to come back to this model and to create sort of hand-labeled data set and check the model. I'll give you an example. Let's say you we took historical data, and that would predict that the customer would gonna churn out, right? Then we put this model into production, right? It predicts certain things, but after a while, you can actually verify if those predictions happened or not, because it predicted that some customers, A, B, C, D, would leave the company within certain time frame, and then you keep collecting the data. You realize that the customers, some of them left, some of them didn't. So that we can use to verify the quality of the model. So in this sense, a sort of hand labeling means you pick up the data that being generated during the business and verify that the model did the correct predictions. And with that, pretty much done with the material. I will usually show you a few books at the end, if you want to go deeper into the materials aside from the book on data science for business that I hope you are reading already. These are some more in-depth books on statistical learning and machine learning. And I see there are some comments and questions here. Let me quickly look through them. Resources, cross-validation. Yes, we can get slides from the lectures. They will be available. Okay. Any questions? All right, so if there's no questions, we're done for today, and you will have seminar with Anvar in 20 minutes, right? Anvar is with us?
Yeah, that's right.
Okay, yep. And so it's a different link for the different Zoom. All right, guys, thank you, and I'll see you in a week.